We're very, very delighted to have our guest today, Dr. Matthias Chung, who goes also by Tia. So Dr. Chung is an associate professor in the Department of Mathematics at Virginia Tech, and also a member of the Computational Modeling and Data Analytics Division and the Systems Biology Division in the Academy of Integrated Science. He joined the Virginia Tech in 2012 and holds a diploma math, which is a Master of Science equivalent from the University of Hamburg, Germany, and a Doctor of Natural Science, PhD equivalent degree in computational mathematics from the University of Lübeck, Germany. Before joining Virginia Tech, he was a postdoctoral fellow at the Emory University and assistant professor at Texas State University. Dr. Chung is a Humboldt Fellow and active member of the Society for Industrial and Applied Mathematics, or SCIAM. Dr. Chung's research concerns various forms of cross-disciplinary inverse problems. Driven by its applications, he and his lab develops and analyzes efficient numerical methods for inverse problems. Applications of interest are widely ranging from many different areas such as system biology, medical and geophysical imaging, and dynamical systems. Challenges such as ill-posedness, large-scale, and uncertainty estimates are addressed by utilizing tools from and developing methods for regularization, randomized methods, stochastic learning, Bayesian inversion, and machine learning. Thank you very much for coming here, Dr. Chung. And without further ado, the floor is yours.
Thanks so much, Sean. It's hard to see with a mask on. Okay, good. I hope you can all hear me. Thanks so much for the invitation, for having me here. It is something new since 2 years. My pens are at least 2 years old, so I haven't done that in person for a long while, and I'm very pleased to have so many nice, interesting conversations already during the day. And I'm very delighted to talk a little bit about my research, which is in inverse problems. And there's always a trade-off. I want to put as much as possible in a talk and tell you about all the exciting things, or at least I think it's exciting to tell you about this. But I narrowed it down a little bit to talk about one particular problem that I can go explain a little bit more in detail what is happening over there. And if we have time in the very end, I'm happy to talk a little bit about some other projects, just very globally, what I'm interested in. Okay, so let me start with just talking about the work is not done alone, with a couple of collaborators. Babak Afgham, he's at TU Denmark, he's a postdoc, and I don't know if any of you know SAMSI. It's semester long, or it's at NC State. It brings together statistics, mathematics, and so on. They have wonderful programs. Unfortunately, it's shut down at the moment, where researchers just get together and work in small groups on particular problems. And that's where this research actually started. We just kept on talking about something, and that's what came out. So multiple other researchers, which you see over here, were involved, and I'm always thankful for support, which I got from NSF and this guy. And the reference I pick on here is most of the stuff you can find over here. And this one just came out in inverse problem last week, I think, so it's fairly new. And if you have the need to interrupt me and have a question, so please feel free, just talk, speak up. I'm very happy to address this. Okay, so to get to the same page, I want to talk about inverse problems. Why did I choose the field of inverse problems? Because I'm interested in many different fields, and luckily, inverse problems lies within so many different applications and fields of mathematics. So what I'm interested in, or what inverse problems is, it brings together physical models and data. and wants to get some information out. That's a general scheme, and that you can do in many different ways. You can think about it a little bit. You need to think about the model, and throughout my talk, please think about your favorite model. It can be a PDE model, ODE model, or some other network model, whatever this might be. Most of them are applicable there. Then I think the connection which brought me a little bit here is about optimal experimental design, because we both actually met, what did we say, about 10 years ago on optimal experimental design. So that is of very big interest. Another big field I'm interested in is inverse problems optimization. So typically what you're doing is you're minimizing a function, and optimization plays a role over there. And something like stochastic optimization is very common now also in machine learning. Uncertainty quantification, if you have you want to get some information out of your system between the data and the system, what is the uncertainty there, right? So this is a part of it. And I think everyone needs to claim a little bit of machine learning with that. So I do that as well. I have some ties to that. And of course, these directions don't go all to inverse problems. They also go in the opposite direction. So they influence also inverse problems. So, and today I basically want to talk about these aspects of my research, and that is in the center, of course, for me, inverse problems, and how can we use machine learning techniques to improve on inverse problems. There are other directions which I would be happy to talk about, this big data problems as well, which goes in the opposite direction. How can inverse problems help machine learning, for example? And if I have time, I'm happy to chat about this anytime. So, and of course, the application area. All right, so that's a global picture. Let's dive into what is an inverse problem. Okay, and a picture says more than 100 words, but let's first say, I have a physical model, right? So I have a forward process, my model, my PDE, ODE, whatever model you have, and it is corrupted with some noise. And I get some observation B. And this A might be also have already some projection operator onto your data space, right? So what I want to get out is what is a good estimate of my X true, my parameter, my model, given B and A, and maybe even some knowledge about my noise realizations, right? So, and you all had that. The easiest thing or the first thing to do is if you have a linear model and it's squared, you just do the inverse and you have your solution. No big deal. And if it's not square, you maybe do a least squares problem, just solve the normal equations associated with this problem over here, and you're good to go, right? What problems can arise? So I found a wonderful picture here on the internet of this building. Oh, no, not this building, it's further down there, right? Let's assume this is our true image. And that one we want to recover from, some blurred image which we have, right? We just took a picture and we want to deblur it. So this operator A is square. So all we need to do is take the inverse and look at what we get out. So taking the inverse, we could just do A inverse B, and that's what you get out. Has not much to do with that. And the blurring operator here, like many interesting problems, is what we call ill-posed. And a problem is ill-posed. We are saying it is ill-posed if a solution does not exist, it is not unique, or it does not depend continuously on the data you're observing. Okay, so that is ill-posed, and that is the main struggle we are having, or this is one of the main struggles. How do I, for example, incorporate some knowledge into the system so that I don't get this problem over here? This inverse problem falls in a big class of so-called variational inverse problems. So I don't take the Bayesian, and whoever is at Bayesian perspective at the moment, but if you think about it, this J could be the likelihood a little bit, and the R could be some prior, and you can maybe minimize the maximum a posteriori estimate. So in variational inverse problem, you minimize some functional, and you want to find some information out of it. And what you typically have is the data to model misfit, what we have seen before, AX minus B, for example, and typically some regularization term, some prior knowledge in a Bayesian sense, which might in turn depend on some hyperparameters. Hyperparameters are defining your prior, your knowledge, and it is, for example, in this way, this is called the Tikhonov problem. Think about this lambda is 0, right? Then you don't incorporate any prior knowledge. If you go with lambda to infinity, then you say, oh, I always think my solution is 0. Right, so, and something in between. So this is adding some regularization, and it is presenting the prior knowledge. And this hyperparameter here, in this case, you see I used a lambda in a boldface, which means there could be other parameters where your prior depends on. And here it's just a single parameter, right? But that's just the simplest case, and I want to explore that. This, for example, this Tikhonov problem, right, where actually this one should be just AX without the parentheses. It's just in case it's linear. If it's non-linear, it's getting a little bit more complicated. But what are the main problems for inverse problems? So you have seen inversion, and just least square solution, maybe incorporating a little bit knowledge from the prior is not new. We have done that many years. But where do the problems come in? And they are threefold. So first of all, if your data is so large that you cannot get either B or A in your memory, or you cannot fully access your forward process. That is a typical problem. And standard methods typically don't apply anymore. There are methods which is called Krylov subspace method, iterative solvers. You cannot apply that if you don't have your full A at hand. That is a big problem we are facing. Let me step to number 3 here, uncertainty estimates. And I mean, there are more proud people here to talk about than me. So typically when you have an inversion and some parameters, you want to know how certain are you about these. That is maybe local uncertainty quantification, but you can think about this global. And what to do at large scale. So whoever did an MCMC before and did some Bayesian inversion knows if I go beyond 10, 20, 100, 10,000, you cannot do so much. It gets much more difficult. And the third one is selecting good priors and choosing a good regularization. How do you do that? This lambda over here looks very innocent, right? I'm showing you problems which are 100,000s or so of unknowns. And there's just one parameter which actually makes a lot of problems. How do we estimate this? Because we don't know this a priori. Okay? And I want to show you here this simple example. And here I plotted lambda, and let's talk about this a little bit. And here the error from the reconstruction, if I invert this, I can just use a normal equation essentially on that for a given lambda and show you what the error is. okay? And you will see if I pick it very small, close to 0, my error has something, it dips down and then goes up. That is very typical. And you want to find essentially a lambda parameter, a regularization parameter, which is very good. Let me illustrate that on the deep learning example, which we had earlier. Let me just see if I can let. You see if I can run it. Oh, there we go. Okay. So the image you just saw before, I just chose different regularization parameters, right? So you start with a very small regularization parameters, and maybe I can just slide through this. You will see you have a lot of corruption of noise in there. You cannot see really anything. Then once you increase your regularization parameter, it gets more bigger and bigger, and it dips down, and the reconstruction is actually pretty good. So this red line here is if my blurred picture, if I would just take the picture I already took. Anything above that doesn't make any sense to look at, right? So, and then if you take a too large picture, you see it blacks out because black is typically the value 0, and I just get a, if I go to infinity, 0 values. Does this make sense? So what this parameter does? And let me hop back over here. So that illustrates essentially what we see in this graph. Yeah, please go ahead.
Exactly what X is for the picture example.
Okay, for the picture example, it is a de-blurred picture. So what the A is the blurring process. Let's assume I know what the process of my blurring is. I take my true image, I blur it, and I compare it to my data. And I want to invert this system, right?
But what is the X? What actually goes into that?
Oh, the X is just the image stacked on top of each other. You are vectorizing it, right? You could also think of tensors in that case, but what you typically do is just think about this as a long vector concatenation of this one. Good question, thank you. All right. So this parameter is very important, and many different approaches have been done already. So one thing is you estimate it directly through some statistical methods. That is a standard way to do that. We looked at a different approach, and that is through a supervised learning. And there are two approaches, and I actually came from that one and went over to this one because I think that is much better. So optimal experimental design is what we think about it is, I want to design a lambda which is good. Okay, so that's where the optimal experimental design comes in. I want the best lambda reconstruction under my lambda, and I see that as an experiment, essentially. Okay, so, but I want to dip down into the deep neural networks and see how that works. But before I do that, I give you some formulas, and I swear you don't need to read these formulas, right? There are some statistical measures how to get a good estimate of the optimal regularization parameters. There are different methods, and they actually just apply for the Tikhonov problem, where you have an L2 regularization term. Otherwise, they don't apply. Okay. So, and there are 3 here. There are more. There are many others. So, the discrepancy principle, essentially, whenever your residual hits the noise level, then you stop. Essentially, this one. And there are some others, and we don't need to talk in detail about this. They exist. And the only thing which I want to point out in the formulas is to get the lambda, think about you need to optimize a function which is one-dimensional. But this Z matrix is an inversion multiplied by that. I need to invert a matrix, and whoever you had in numerical analysis should probably tell you never invert a matrix if you don't need the matrix, right? So because it is just so expensive. So this, to get one evaluation of the function is extremely expensive already. And it overpowers just the pure inversion of the entire problem, just to get the one parameter. Okay, so that is a major issue. We want to speed this up, and the entire point of it is we want to learn it prior to that. Okay, let's talk about optimal experimental design. And my viewpoint is now a variational and not the Bayesian approach. So which boils down to a bi-level optimization problem. So which says, minimize this one here for some lambda, given lambda. And now I update my lambda dependent how close I'm to the true solution. If I'm training, I have the true solution. I have some training set. Okay, so I'm minimizing over minimizing. This is a bi-level optimization problem. And whoever did a bi-level optimization before? No, you did. Okay, it's nasty. It's really nasty because if you have non-convexity in here, you have non-differentiability here, and not even non-differentiable and non-continuous. So it's actually pretty bad. So this is not necessarily so easy to do. Nevertheless, we use this and it can work pretty well. And Eldad Haber has done a lot of work, and you have done a lot of work, not on this problem, but on the Bayesian framework with Youssef together. And yeah, there's a lot of material in there. So what you're doing is you have a data set, X true and B, you're training on that, and you get some lambda hat, and that you use now for your inverse problem if you get new data in. Okay, this has one disadvantage, and that is whatever new data you get, you will always use the same lambda. It does not adapt to it. Right? So you are learning just one value. And our idea was to say, okay, let's not just learn one value. Let's learn the function, essentially a mapping. And that's exactly what neural networks do. Okay? So let me go through a nasty neural network page, and I view everything from linear algebra, from how does it look in linear algebra or functions. So what I assume, and that is the underlying assumption over all supervised learning essentially, is that I have a mapping from my observation to some target. Here it's for me lambda. I want to learn lambda. And this is not a neural network. This is just whenever you give me data, I can get some information about my lambda out. Okay? And all what a neural network does, the only thing it does, it says, I'm creating a function with some parameters to make this mapping. And all I need to do is learn these parameters. That's all a neural network does. And these neural networks are not any kind of function. They have certain structure. And that is typically a concatenation of functions which have a linear part and a nonlinear part. And they are just going in hand. And you have seen all these pictures with all the neurons. I rather like to see, I have something over here. I plug it into these matrix vector with some nonlinear function over here. I get it to the next level and so on, and I get some output. All of it is just a big function mapping from the input to the output. Okay, so, and in our case, we have our neural network, which is this one over here, and our output. We plug our input in and look at our output. And how do we learn the neural networks? By our training data, right? We're looking what is the input and what is the output, and just now start to learn how this mapping works. This is all okay? Please go ahead.
Just a question about your regularization. So, when you train neural network, you can also add a regularization. And it can be also be affected by another lambda. So what if there's also an optimal lambda?
Yeah, there's always a tail underneath, right?
Yeah.
There's always a string underneath. So here I actually don't need a regularization because in our problem, this is fairly well posed. It also depends on the network you're using. But you're right. You can have hyperparameters which have parameters again, right? Hyperparameters. You can have an endless chain over there. It's a philosophical question where to stop, right? And how much influence does that still have? Yeah, please go ahead.
To build off of that question, so can you, depending on your application and the situation, set like this is the limit that I want to go to in terms of this specific lambda, and then you go from there instead of like, oh, I want to go to the next more precise lambda.
So typically you make it, so that gets a little bit in a philosophical question where to stop there.
Yeah.
Because what you do is you are including some prior knowledge. Typically in a Bayesian framework, that should be independent of whatever you've seen. You haven't done any experiment, that is your knowledge, right? And now you are saying your knowledge depends on some hyperparameters. So that makes a problem broader. And think about it, as more broader you make it, and less information you have.
So you should use more problems.
Yeah. Make sense?
Yep.
I have a question.
Yeah.
So in the setup here, is B your entire training data set? And you're saying if you have this training data set, you should pick this lambda. Is that the setup?
Yeah, that's exactly right. So the BJ is one data point, and I take a data set J from 1 to J. And I'm here looking at the regression loss, right, where my network gives me a good lambda. And there are many loss functions, but here the regression loss makes sense since lambda is typically a positive, or in this case, I think I took the squared is some real value in this case. But as I did it bold again, it does not need to be one parameter. It can be multiple. Okay, so it could be hyperparameters. If you're familiar with Matern kernels or some other kernels, they have multiple parameters which you can tune. And they could be in this lambda over here. Yes.
So, slightly different.
Say again. So
is there any hope in trying to denoise of the B so that the regularization and B those problems very closely?
So you mean directly from the B to the denoised one?
Yeah.
Then you would learn the entire inversion map, right?
Yeah.
So that is a very good question, and that's actually a big chunk of work right now. It's inverse, what is called inverse neural networks and so on. They want to learn this mapping. I specifically don't want to do that, and I can give you why I don't want to do that. I don't want to eliminate the physical model. If you have knowledge about your physical model, you should somehow include it, right? So, and I want to just help the physical model essentially to include the prior. Because if you do what exactly you've done, and it's exactly what people do, right? You take your B and you get your X out. The mapping exists, but you reduce your physical model, it's not there anymore. And what you're doing is you're going from dimension B to dimension X. And an imaging application, this is extremely large. That means the entire learning the network is extremely difficult, right? Is it a good answer to that? Okay, great. All right. Any other questions? I don't check anything online. Shuna, I don't know if you see. Okay, good. Good. All right. So what we are doing is the following thing. So this is the entire method, right? Okay, I have some forward process, I have some noise and some true X. And that I gave the deblurring as an example. There are many different other examples, right? So I generate some data, BJs, and I obtain the lambda opt, the optimal lambda you have seen. And you can remind me later on, I'm cheating here a little bit. Not really cheating, but I don't say everything there. So I set up my neural network, whatever structure you want, okay? And now I use this tuple to, or the set, to compute my parameters in my neural network. And this one is all in the offline stage, right? Now in the online state, all I need to do is a forward propagation of my network. I plug in my new B, whatever image you have, and I know what the regularization parameter is, this lambda. That means I have a mapping that is a function, right? For every new data set I'm getting a new lambda. So which is better than just getting one lambda, right? For all problems. Okay, and then given that lambda, I still use my physical model to invert. Okay. Let me go through a very simple example first, and I don't want to go into all details. This is just some random, not random signals, some signals. This would be a true X, right? And I take a heat equation, which is a linear forward problem. It's ill-posed, so you're getting these observations. And what you want to infer this one, right? So, but you need regularization on that. So the A is ill-conditioned heat problem. So we take some noise, and actually this is also something, I don't pick one noise level. I pick many different noise levels. So let's say I don't know what the noise level is. I pick just many. Who cares? I have a neural network, a black box, which learns this, right? And I look at the Tikhonov problem. Okay. Of course, if I propose a new method, I should compare to what exists. So these are the three statistical models over here, and I crossed out the discrepancy principle because that performs so well, badly in this case that the graphs will not look pretty if I include that. Okay, so I use the optimal experimental design approach, and two different networks here. DNN is just a deep neural network, and ELM, you can think about a regression model. It's a linear neural network, which is just one layer. And so, there's a big fuss about extreme learning machines and so on. I don't want to go into details. You can call it regression. Okay, so it's a very simple model, like this. I take this simulation data for optimal experimental design, and B and lambda opt for my neural networks to learn both of them. Okay, and the structure of this is a simple, fully connected feed-forward model, so straight there. So what do I show here? And that's a little bit small. I mean, it's so great to have now some technology to easily zoom in, right? This on the left, I show the discrepancy of my output, right? From my optimal regularization parameter over different approaches. And I plotted the density, right? And you want to essentially very close around zero. You want always to hit the zero the best. So what do we have here? So UPRE and GCV, you see they underestimate actually the regularization parameter. It's more to the left. OED, optimal experimental design, does actually pretty well over here, right? So that does pretty good. ELM as well, but if you have a deep neural network which has some non-linearities in there, it does pretty extremely good. And we are not only interested, we are not interested actually in what the good regularization parameters is. We want to see if the reconstruction is good, right? So the inverse solution, if we use these regularization parameter, and this black dotted line is the best you can do with a regularization technique. Okay, and then you see where it heads off. And of course, I wanted to point out the neural network. There's essentially no difference. It's minimal worse, right? But it pretty much always hits the optimal regularization point. For data, you haven't observed yet. So that's all for validation data. Okay, so that was very impressive to us. And we said, okay, we can do that on other problems as well. And let's look, let's first, talk a little bit of what are the advantages and disadvantages of different methods. The direct methods, as I already said, right, they have, I don't need any training data for that, of course, but it's expensive to compute because you need to do it online. OED has, you get actually pretty good estimates, right? But it does not generalize as well as a neural network. As I pointed out, the bi-level optimization is a problem, and you just get one for all, one regularization for all data. So that is a disadvantage. However, because of this, you can actually apply this for higher dimensions. Your lambda can be extremely high dimensional. For the DNN, it can be problematic. We haven't fully explored that. So DNNs give you pretty good estimates, and even for individual data, and it trains very well, but it needs training, right? So, any questions for that? So let's look at tomography problem. Computer tomography, here a parallel beam. You have an object, and here it's a Shep-Logan phantom. I don't know if any one of you have seen that before. What you're doing, you're shooting X-rays and measure essentially how much comes out at the other side, and then you're rotating this entire device, and by the Radon transform, or by the inverse Radon transform, you can reconstruct the image. Okay, let's assume this is a true image. That is, as I said, the Shep-Logan phantom in here, and this is the sinogram. This is essentially you're shooting out, you're measuring over here, and you're putting the data in one row. And that's how you collect the data. So, and out of the sinogram, you want to reconstruct the image. This is a linear problem, as you see over there, a X transform, linearized problem, to be correct. And this matrix actually is ill-conditioned. So we have an ill-posed problem, and we need regularization. First of all, what I want to point out is the regularization term here, that is over here, is an L1 regularization. Did anyone try L1 regularization before? So what L1 regularization promotes is sparsity in your solution. And here we use sparsity in the derivative, right? So that is here, as you see, the image is fairly constant over here. So the derivative should be almost zero there. Just in the few points, you have some derivative. So what L1 or regularization with this derivative or difference operator does, it's called total variation. It promotes sparsity in your reconstruction in the derivatives. Okay, so, but this one has still a regularization parameter in there. Now, all of my standard regularization estimation methods are out of the window. They don't apply. So you're ending up with different concepts, either even more expensive one, or you're trying to learn it. And that's what we did over here. First of all, to invert this, you need also an iterative method. Here we use a split-Bregman or ADMM, however you want to call this method, and it helps you to solve it. You cannot just invert it anymore. Okay, so here are some test and training images, how it looks like. We take a randomized version of the ChapLogan to create our data set, so our training data set. And since we are working on images over here, we take convolutional neural networks to make the networks nicer, not so high dimensional. We can go deeper. And this is just some more information about the neural network. To be honest, the design does not matter so much. The mapping is extremely good. There is somehow a very good mapping between the data and the choice of the regularization parameter, which is not analytically, we don't know it, but the neural network can pretty well approximate that, okay? So, and we use standard methods for optimizing, finding these parameters in the machine learning. And what I plotted here is two sets. So first of all, here's the optimal regularization parameter, and here's the estimated. The identity line would be, I'm hitting always the optimal one, right? The blue one is a DNN, the deep neural networks, and the other one is just a standard neural network, so ELM, just a one layer linear model. And the DNNs learn so much better over here. And that you will also see over here, the discrepancy is very small. Let me zoom in, because I want to zoom in the other one shortly. This one over here, okay? So we have, again, close to zero. You want your density mostly close to zero to show your network is doing pretty well, while the ELM has a much broader densities. So, but we are interested in the reconstruction. How do we do with the reconstruction? And that looks pretty good as well, right? If you see, we have the true and black, and the blue is fairly close fitting over there. And now comes something very interesting, which we observed. I don't know if you see that, but it's not there, but up here. You see, the density of our DNN is better than the optimal one. How can I be better than the optimal one? That is impossible. Think about, we need to compute the optimal one as well. We pre-compute this, and we use an iterative method to do that. What we found out that the DNN predicts better than our optimization method did for the optimal one. We found points where we didn't learn the right optimal regularization parameter because it's not necessarily a convex problem. So we just didn't find it. So in some cases. So, and we observed that DNN can actually do pretty good, more than optimal regularization parameter. Now, that's not true, but more than we can optimize it. Okay. So I don't want to go into most of the details. This is just, we tried it for different application, and I don't show you all the application. That was essentially it. This one is just different. It's a deep learning example where we look at inclusions, well, like cancer inclusions and so on, and we want to look how it is spreading essentially. We want not only to know the regularization parameter, how to reconstruct it when we find it, but we also want to know what is the outline of this one and how spread out. So and we learn exactly these things with the neural networks. The results in general were pretty good as well. Here you see the DNN as well for the regularization parameter, and this parameter is the second parameter, which shows you how smooth essentially your inclusion is. And we can learn that pretty well. Here, not as good as we did before, but I mean, there's a lot of tuning we could do still, and the results are, at least for us, pretty convincing. I still have the diffusion problem in there, but I essentially want to skip that because this is just a third application and I don't want to bother you too much with that. Since we have just, how much time do I have? Just 5 minutes. Oh, 10 minutes. Oh, I can talk a lot. No, I don't want to do it too long, but I want to point out some other projects I'm working on, what I'm interested in. And I showed you in the beginning that I was machine learning inverse problems in data. This is an interesting application where we talk about surrogate data. And you all have heard about, no, I assume that, sorry for that. Assume you might have heard about surrogate modeling. For example, in a neural network, you have a physical model, you train your networks to perform as your physical model, and that's typically called a surrogate model. Can do that also for with Gaussian processes or stochastic processes. We looked at something different, and I lost connection somehow. Oh, there we go. Sorry, just some delay. What we looked is surrogate data, and I want to look at here a dynamic system just for illustration. Think about you are taking some measurements, right? And you want to include, you want to know some uncertainty, you want to quantify the uncertainty, and you want to include prior knowledge. With dynamical systems, you often don't know what these parameters are. Right, so some growth parameters, and you often know they are positive and so on. But any prior knowledge on that is not much. Certainly, just some ranges. However, you know oftentimes something about your dynamics. Think about you have some data in a time process, and you're measuring at certain times. You know, if you have a dynamical system, that the data in between is at least C1, continuously differentiable, because you have a dynamical system, right? So, and we thought about how can we include this knowledge that we know that is continuously differentiable in between data points. And we do that through so-called Gaussian processes. So we are building a Gaussian process around this data, right? So you get a mean and a variance at each data point. And now I can throw away my data and use my surrogate data as my real data. The nice thing about this is that you can have as much data as you want. Right, because if you can think about it, I'm interpolating, but I'm also including some statistics about what my behavior is in between. So this is essentially just a posterior fit of the Gaussian process. But now I do parameter estimation with that. Now I want to find my parameters, and my density goes extremely down. I don't think we can even see that there's some gray one maybe in there. So I'm pinpointing essentially my parameters which I want to estimate. And let me not go into all the details. This is just a comparison over here. That is the estimate. That's an MCMC, what I did. What you do see is a standard MCMC for the parameters. And using just surrogate data to estimate the parameter gives you a high density around the true parameter. It's pretty impressive what you can do that with, including really surrogate data exploiting the differentiability, for example, of your model. Okay. If that was a little bit too fast, I just put it in a snapshot. Otherwise, I would talk too long. I'm happy to talk about this. This is an exciting project. Another project, which I just want to show you the results, is on stochastic optimization. So what if your model is extremely large, you cannot get it all in your memory? So then you need to use some stochastic optimization method to deal with that. And I want to illustrate this on another tomography problem, and just to show you what we can do on a desktop. So if we use the stochastic approximation methods and using some knowledge from the inverse problem theory, this is a matrix you see. It's 260 million by 100 something. That's 10 to the 15 entries or something like this. Of course, it's not dense, but there's no way you can get it in a desktop machine, right? So at some points, not even the data. So this is a 3D tomography problem, what we have over here. So what you've seen before, you now take images from each direction, and you want to reconstruct the volume. And we want to reconstruct a volume which is 511, 511, 511. That's not really that big, right? But that is a matrix which you need to work with. So here we compared essentially to SGD, stochastic gradient descent. And I follow some people who don't want to call that a descent because stochastic, this method are not necessarily descent method. Then there are methods which are a little bit more advanced, and these are stochastic or sampled limited memory BFGS methods. So they are incorporating some kind of curvature information. It is not easy in stochastic settings to do that. And we propose another method, which is called SlimLS or SlimTick, which is a sample limited memory method. And I just show you this for a linear case. We do that now for neural networks as well. And the paper should come out today or tomorrow, I hope, on archive on that. There's some exciting work we have done. I don't want to praise myself. So the postdoc did all the work. So no, it was really exciting what the results are. We have very fast conversion even compared to Adam. So that's something like your 3D volume, how it looks like. These are your projection images. There you have, how many did we? 1,000. 1,000 images. Did we? Yeah, 1,000 of these images. And these are essentially the convergence, how I go to get my reconstruction. And you see SGD and some BFGS time of matter and sample limited memory least squares methods. Okay, and with that, I think I should close and just tell you again that I'm very excited to be in person somewhere again after a long period of time and to present you some of my research. So if you are interested in that, I wanted to convey, so inverse problem can be very central, and there are interesting things you can do with that. Either in inverse problem, I use inverse problem to essentially get out and use for other areas. So there are a lot of things as non-linear least squares. I just talked about linear problems. There are a lot of other things I talked about, not about the following. This is a step size selection and machine learning. Whoever did this before picks 0.001 for the atom, and that's good, and maybe some decay. But we are working on adapting the learning rates because they have a connection to regularization parameters. There is a tight connection, and we are exploring that. And of course, I'm always interested in nonlinear model, physical models, some application where we can use this method and where they can enrich the research as done, for example, in engineering. So thanks a lot for your attention, and I'm happy to take any question.
Thank you very much for a wonderful presentation here. So yeah, maybe let's take some questions. There's also, I see a quick one, maybe we want to pick
Sure.
up here directly and maybe read out.
So what was order of convergence for, oh, yeah, I mean, they are all the same order. They cannot be different because they are restricted by, well, square root of n or so. That it's always the same. The same. You cannot, with stochastic approximation method, you cannot go faster than that. The order is the same. The question is, how do you pick the regularization parameter or the learning rate? Let me just explain that in the following way. And it's what your learning rate does is you learn in a certain direction and you want to get the information of that direction out, but not go too far to get noise in your system. And that is exactly what the SlimLS and these kind of methods do, that they incorporate what is the noise and what is the real new information I get from this direction. Does it answer the question? Good, thank you. Uh-huh. Mm-hmm.
So did you compare with the map, also using the network, a map from the measurement B to the original, to the target image X directly?
So I think that's very similar what we talked about. We didn't do that. You can do that, and it's very interesting. That's essentially a surrogate inversion, yeah. Right? You're replacing the entire inversion process. With medical CT imaging, I wouldn't recommend doing that because, I mean, you have a physical model there, and I'm not necessarily hopeful that you get very good results. You need a big training because you are going from n squared to whatever dimension it is, right? There are a lot of parameters for you to learn, and it can be difficult. And you're throwing away your physical model really in that. And that's what I'm afraid of. I think it's a great idea and it's good to incorporate, but not in every single application, especially where your physical model, you want the physics in there. Yeah, so you don't want a surrogate model for flying to the moon, right? You want the physics in there. Does it answer the question?
Yeah, because I saw some paper that do that directly. So
yeah, they do it directly, and then sometimes they have some good results, right? They definitely show it, but I'm careful about this because you're throwing away the physics. But there are also the physics-informed neural networks. You can think about incorporating physics as a regularization again, right? That's what people are now doing. You can do that, or other people in your group, you're learning the discrepancy between the model, and I mean, there are a lot of new ideas in there. Yeah. But that here we really wanted to just to focus on the prior.
Do you face issues where your training set, you develop it with a simulated version of the physical model, and then your real experimental data has artifacts that you haven't predicted or haven't simulated in the training set? Mm-hmm. Are there issues that arise from those differences?
Thanks a lot for bringing that up. I should have brought that up because that was a reviewer who did that as well. How does it generalize about the training set or pictures you haven't seen before? And I generated this talk before all that, but there's a picture in the reference where we tried it on a set which we haven't observed, and it worked pretty well. Does it is real data, so it's real data which we talk. So it's a CT of walnut. So that's from a Finnish group who do all the real CT scans. We tried it on this data set and it was pretty good.
So I have my data, it's X-ray as well, not images.
Mm-hmm.
Interaction with a lot of unpredictable things
Mm-hmm.
that intensity changes and noise.
Mm-hmm.
I'm wondering,
So you.
how far away can the building be from?
That is a good question. That is not fully explored. We haven't done that, right? So we just did an reviewer ask us, how does it work? And we said, let's take an image which we haven't seen, which is not Shep-Logan phantom or so, and the prediction was pretty good. But you're right, and I told you, I think earlier, to point me to that, because I put something under the rug, and maybe I should at least catch myself there. Let's see if I can quickly find that. Where was our algorithm? I had it somewhere. There, right? So, and it's exactly this line over here. So what is the optimal regularization parameter? So I need to compute this, right? And I said that in the end, that is not even a convex problem. There could be multiple, and it's computationally expensive. So all of this setup is extremely expensive in the beginning. So we are looking at what if I don't know the optimal, just some other ideas how to improve on that, and we're working on that. That's also, how do you set up your training data? You can think about it in your, what did you say, different refractions, different areas. That's actually what we did with the noise level, right? We just didn't look at just one noise level, we took a bunch of noise levels. And that you can extend, in your case, to different, sorry, I've got frequencies or different parameters to explore more, to train your network better. Diffraction parameters, yeah, that's right. But yeah, very, very interesting.
We have a question online here.
Okay, what would be the best approach to choose the prior? Oh, yeah, no, that is so. A functional form of the prior. I assume that is our the question. That is not easy to answer, right? So. If I'm going to geophysics, for example, right? So there you have a class of the Matern kernels, which is a class of priors you're using where you don't know the hyperparameters. They are choosing these hyperparameters because the Matern kernels are, yeah, it depends on the parameters, but are not continuously differentiable, not smooth functions. They have certain edges. And if you have images of the subsurface, then you have these layers, and you want exactly this represented in your priors. If you're going to medical imaging and so on, that might be very different. Often there's L0, you want to have the L0 norm, which is approximative L1, which promotes sparsity. It is very dependent on the application and can be very specific. There are several problems with remote sensing, for example, where the priors are very particular. And we tried it on some remote sensing problems. What was I don't recall the name of the satellite. GOMOS project. I don't know if you heard of this GOMOS project. So they essentially want to measure the atmosphere, the chemical content of the atmosphere. So they are they have observation of a star through different layers of the Earth's atmosphere. And that is very noisy. And to filter this out, you need very good priors and very specific priors. And yeah, it's a very difficult question and very hard to answer, I think. That's all I can do, I think. Is that appropriate? I hope so. Thank you. Okay, good.
Questions for Dr. Chung? Okay, if not, thank you all very much, and let's thank Dr. Chung again for a wonderful.
Thank you.